Hi. So this is one of the experimental data that I got after cycling for my systems. I'm going to show you how we can fit using the EIS fitting model. So first go to the analysis, electrochemical impedance spectroscopy, and then jet fit. So when you get this window, you need to set up some parameters like fitting method, iteration value, and the circuit model, which circuit you design. All these three things will be do some trial and error using those value. This is x square value and x over square root of n is the number of cycle. These two value actually have to be below 1. As lowest as possible, you will get the smooth fitting, which actually match with your experimental data. So when you select the fitting method, there are several fitting method. You can do the trial and error process. For the sodium metal systems, I use randomized and simplex method, and then I saw the previous researcher, even in our group, they use this randomized and simplex method for lithium metal systems. And the iteration value, I use the maximum iteration like 5000, which actually fit smoothly to the experimental value. And some people use 100 iteration. It depends on you how these two value you get the lowest, and then if you think that this is matched with, and then you can accept it. And then the last one is the circuit model selection. So when you get this window, you will see there are a lot of predefined circuit you present here. Like this is 2-component layer model, this is 3-component layer model, this 3-component with Warburg diffusion, this is 2-component with Warburg diffusion. If you think that your desired circuit is not there, you can actually design by yourself using the graphic editor. And then when you design, you need the elements. So all the elements actually present here, like this is the resistance, this is inductor, this is capacitor, this is the Q, constant phase element, and this is the Warburg diffusion. So which one you need, and then you need the linker, like this is the serial, this is parallel split and parallel joint to complete the circuit. So when you think that, well, I no need this Warburg diffusion, you can actually delete it. And then you can first you can draw it. First use the parallel split, you can design circuit here, and then finally you can link here. But I will do this way. This one will add here parallel split. Now I will give a component like constant phase element, one of the component here. And then because resistance should be parallel, so it should be here. And then I will use the link to finish the circuit. So do it here. And then if you think that, well, diffusion will be here, so you can use a Warburg diffusion, you just add it. You can redefine all over. I just show how you can do it. So after you finish your circuit, you need to select whole circuit, and then you need to align it. Right button, align. So this all will be aligned. And after that, you can just copy, right button, copy, and then you paste it to the PPT or wherever you want. And you can redefine your equivalent equation, circuit equation. So this is Q4 over R4 plus Warburg diffusion component number 5. So this is this is the way you can do it, and then click OK. Because for my systems, I find these two components with Warburg diffusion perfectly well. I just do the OK button. So once you select your equivalent circuit, you give the iteration number and then method, you can do the minimize button. So sometimes it take a little bit time. So once I get it, I will show you how we can get all the information from the here. So we need to set up, like I will do the first value should be start from here, because this is imaginary. So I'm now going to show you how we can get the information after the fitting. Let's say this is the fit, because it will take time if I want to adjust it. So you will get the value. It should be below 1 definitely. And then how you select your resistance value. The three component R1, R2, R3. So you always remember the R1 value is the solution. The first R1 should be the first resistance will be the solution. So R1 will be the solution resistance. And for R2, R3 component, how you select which one is the is your surface resistance and charge transfer resistance. Because whenever the ion movement is start with, it gets the resistance from the solution and then gets the resistance from the surface layer, I mean interface, and then it gets the resistance from charge transfer. So the R2, R3 you can get here. You can see this is A2 value and this is A3 value. Which value is the lowest value? That will be the lowest value one will be the lowest value corresponding. R3 will be the surface interface resistance. So they let's say this is correct. So A3.04 and this is A2 is higher. So corresponding R2 R3 will be the interface resistance and corresponding Q3, and then this R2 will be the charge transfer resistance. Now you need to do quite several time iteration with the similar keep the similar thing, because you need to get the error value, how much error. Because every time you see the this value, let's say 53.78, next time you will not get the exactly same value, it will be little bit change. So this is the way you can get the error value. And then I forgot to ask, this A2 and A3, these are the constant. If you want to know more, you can get the EC Lab manual software. You can help. And then there is the user manual here, so you can go and then find those all the information. And finally, from this model fit, we can actually calculate the thickness of the interface, ACL layer thickness and the capacitance. So these two values equation I will show in the PPT. But one of the information need to get it from here is the CO2 capacitance. So let's say these are the correct. So C2 and C3 will be the corresponding corresponding pseudo capacitance. So let's go back to the PPT.